Before we discuss the properties of silicon, let's discuss the atomic structure very briefly. A silicon has 14 neutrons and 14 protons and of course 14 electrons as well, because number of electrons and protons are usually equal for a neutral atom. So now I will just make the basic atomic structure of silicon. So 14 neutrons will go to the nucleus. Similarly, 14 protons will also reside in the nucleus, and because of that, nucleus will have a positive charge. And according to the rule we have studied, that the first orbit will be occupied only by 2 electrons, and no more than 2 electrons can occupy this first orbit or shell. The second shell will have 8 electrons. If you remember the rule, 2n squared, and now here n is 2, the second orbit from the nucleus, and 2 squared 4, 4 multiplied by 2, 8. So now I will place 8 electrons in the second shell according to the scheme. Electrons are distributed. So now I have 4. I need to place 4 more electrons, 3 and 4. So now second shell is full. I can't put more electrons into it. So I have to go to the third orbit. If you remember the third orbit, 2n squared, 3 squared 9, 9 multiplied by 2, 18. So the recommended, or for the maximum stability, the recommended number of electrons should be 18. But unfortunately, I have only 4 electrons left to me, and I have no choice but to place them in the third orbit. So this orbit is once again not complete. There should have been 18 electrons, but now there are 4. So this shell is once again not completely filled, but at the same time it is not completely empty. So it is somewhere in the middle, and this property makes it a good semiconductor, which we have already discussed. In that case, we discussed the properties of boron, but the behavior is similar, so you can connect the ideas. That's why it makes silicon the favorite semiconductor material, because it is available widely on earth and it's easy to process it. That's why it's very famous in electronics as a semiconductor. And of course, there should not be this orbit, because that orbit is required for higher atomic number elements. So this is the atom of silicon. And don't forget that in the forthcoming discussion, when I will refer to a silicon atom, I will represent this complete picture of a silicon atom like this. I will hide all the inner shells and along with nucleus, and I will show this whole part along with inner shells and nucleus as a central part, and I will only show the outermost shell and its electrons 4. So I will present a picture of silicon like this. So keep in mind that in the central part, nucleus and the inner shells are just hidden, so that I can present a good picture, because we are interested only in the valence electrons, and we want to deal how do they interact with other atoms when I want to present a solid. A solid is, roughly speaking, a periodic array of atoms arranged along a line, and we want to see the interaction. So I will present this picture, just remember it. And also remember that in this picture we don't know what is the outermost shell. For example, in this case, this outermost shell is M, or the third n is equal to 3. We usually don't need this information, but just keep in mind that when you are comparing, for example, two atoms for example, electron deficiency or something, then this picture doesn't tell you what is actually the outermost shell, whether it is M or N. If you are comparing two atoms, for example, then you must have same outermost shell at least to have a good reference. For example, if you are comparing two atoms like this, picture will be like this for both, but maybe for one it is M and for the other it is L, so it will not make a good comparison in that case. Just keep that information. We usually don't need that what is actually outermost shell. We only care about outermost shell and number of electrons in that shell. And of course the recommended number of electrons is also a very important quantity, and you will only know the recommended number of electrons when you know that what is the outermost shell. For example, is 3, and we know that 3 squared 9, and the maximum number of electrons for this outermost shell are 18, and then you can make a good comparison that out of 18 we have only 4, and how much is the deficiency of electrons in that orbit. Similarly, another popular semiconductor is germanium. It has 41 neutrons, 32 electrons, and of course 32 protons. So I will go very quick. I don't need to make the structure myself. I have already done it for you. There are 41 neutrons and 32 protons in the nucleus. Then according to the scheme, I have 4 and then 8 and 18 electrons in the first, second, and third shell, or K, L, and M shell. And in the outermost shell, which is now N, I am left only with 4 electrons, so I put 4 electrons here. And remember that the recommended number of electrons for the outermost shell, or N shell in this case, should be 32, because according to the rules 2n squared, and this is the fourth shell, so it's 32. So out of 32 I have placed only 4 electrons. But according to our agreed format in the forthcoming discussion, if I need to show the germanium atom in a solid, I will show it like this. So because in our compact form representation of the atom, I told you that I will not show the inner completed orbits or shells along with nucleus. I will only show the outermost shell electrons. So I will once again show germanium like this. And let me clarify one confusion, that the representation of our agreed format, for example here, this is same for silicon and germanium. So if I am referring to silicon, for example, in the discussion, it is equally applicable for germanium as well. Because you see, silicon and germanium both have 4 electrons in the outermost shell, although the outermost shell is different for silicon and germanium. For silicon, it is the third shell. 1, 2, and 3. It is the third shell. But for germanium, it is the fourth shell, and there are 4 electrons. But because in our compact representation of an atom, we don't care about the inner shells, we will only show outermost electrons. So the representation for both will be the same, but just keep in mind that it is not same in terms of shells, because there are these 4 electrons are in the fourth shell for germanium, but in the third shell for silicon. But in the forthcoming discussion, because we only want to see the interaction of these outermost electrons with other similar atoms, so it won't affect uh, any problem. And in the forthcoming discussion, it should be easy to understand what's going on. Okay, so now let's see the behavior of silicon. Before we saw the behavior of boron, and I didn't discuss in more detail the interaction of different atoms inside the material, because when you make a solid from a material, the atoms, they come closer to each other, and then the atom is not an isolated atom. It has influence from the neighboring atoms, and then we have to see what is the interaction, and this interaction is usually expressed in terms of bonding between the atoms. For if you remember, when we were talking about the conductors and we specifically talked about copper, we saw that when these atoms of the copper, they come closer to each other, we saw that a type of metallic bonding was formed in that case, because there was only one electron in the outermost shell in case of copper, and then every atom was sharing its outermost or the valence electron with all the other atoms. So it was like electrons are moving everywhere, because this, for example, this atom was sharing its electron with all the other atom, and same was the case with every atom in that material. So now we want to see what will happen for silicon. We know the structure of silicon, we represent it like this, that it has 4 electrons in the outermost shell, and because now the outermost shells are not completely filled and they are not severely empty, there are some electrons, and if you remember, the outermost shell for silicon was the third, and for the third there should be 18 electrons in an ideal case, because for the third 2n squared rule says that there should be 18. But now let's see what will happen. So now there are 4 electrons in the outermost shell, and then a different kind of bonding is formed between these atoms. In this bonding is called covalent bonding, and what happens in this bonding is that every silicon atom, for example this, it has 4 electrons in the outermost shell. Let's take the middle atom so that I can show all the interactions. So it will share its electrons with the 4 neighboring atoms. For example, this, it will share this electron with the neighboring atom to the right. So these electron will move here. For example, electron of this atom may go this way, and electron of this atom may go this way. And similarly, then that electron will go to the first electron way, and the first one will follow this way. So it is like they are moving like this all the time. So this atom is sharing 1 electron with the atom to the right. Same is the case with the atom on the left side. It will share this electron with the atom towards the right, and that atom will also share an electron with this atom. So they will move like this, and the other will go like this. It's like moving with them. Similarly, it has 1 more electron. It will share with the outermost electron of the atom on above, and same is the case with the atom below it. So this type of bonding is called covalent bonding, and every atom will share electron with only the neighboring atoms. So you see the difference between metallic bonding and covalent bonding is that in the metallic bonding, every atom was sharing its electron with all the atoms in the material present. It was not, but here it is bit restricted. An atom is sharing electron only with the neighboring atom. For example, it is sharing 1 electron with the atom on the right, another electron with the atom on the left, 1 with the atom above, and 1 below. So it is a limited type of bonding, right? And then you can understand the behavior of semiconductors, why they are semiconductors. Because in coppers, electrons were almost free. They were just wandering around in the whole material. For example, this one was wandering here, and then it would go here, maybe there, and then there, and it is the case with all the electrons, with all the atoms. So their movement was like they're almost free. But here it is restricted because of covalent bonding, because now they are shared only with neighboring electrons. They are not moving in the whole material freely. And because of this, when you connect terminals of the battery under normal conditions, for example, negative, and here is the positive terminal, so you will not see flow of current in the circuit. So here is a clearer image of what is going on inside the material. When a solid is formed, you know that it is actually a periodic array of atoms. So atoms are like distributed along the lines. So here is the silicon atom, and we know that there are 4 outermost electrons in the third orbit. and these 4 electrons are shared with all the neighboring, only with the neighboring atoms. So let's take the middle atom, because then I can show you all the interactions. So it will share this electron with the neighboring atom, and the neighboring atom of course will share its electron with this one. So if this electron moves this way, this one will go this way. So in this way they are just moving like this. So if I draw the shape, it is like this. So one is moving this way, another is moving that way. Similarly, this atom is also shared with the atom above it, and it is shared. Similarly, a covalent bond will form on the left side and below it. So a similar situation will occur like this. So this atom will go this way to be shared with the atom above it, and the electron of the above atom will go down to be attached for this atom for a moment, and of course then it will go up, and this will go on. And this is called covalent bonding, and because of this bonding it will not let electrons move through the material freely, because now the electrons are bound with their nuclei, at least 2 nuclei in this case, because they will not leave their nuclei so easily, unlike the case of metallic bonding. And then you can extend this picture. Of course, the atom, this image will just keep going like that. Every atom will share its electron with the neighboring atom. In fact, all the 4 electrons in the valence shell with the 4 neighboring atoms, and you can extend this picture easily. Of course, when you reach at the end, you will see some electrons are left from bonding at the edges, but they won't contribute much in determining the conductivity of this material. So in that case, now you see that if the electric field applied across the ends of this material, the electrons will not easily flow through it, because now they are bonded with 2 or among 2 neighboring atoms, and it will not be easy to force them to flow through the material and go to the other end of the body unless you do something. And what you can do is, first you can either increase the potential difference across the body, and I told you it is not practical. Similarly, you can heat the object to give extra energy to these electrons so that they can detach themselves from these 2 neighboring atoms and they can flow. But we have another smart way to deal with this problem to control the conductivity, because we want it to conduct in the normal conditions. For example, at 0K, it will not conduct. And if we want to make it a conductor, or if we want to have a control the conductivity, there is a smart way to do this, and that is the topic of our next discussion. And every time when I say that when you form a solid, and a solid is a representation like the atoms are arranged in a series like this. So more specifically, it is crystalline structure of the solid in which the atoms form a periodic lines like this, because there are many types or few types of solids, and one is crystalline structure. So specifically this is crystalline structure of the solid in which atoms can be represented like a series like this. And of course it is not 2-dimensional, it is 3-dimensional. For example, you can consider that a similar structure is present behind these atoms, a mirror image behind this, and then another behind this, and then another behind this. Of course it is a 3-dimensional material. Now it's time to talk about the valence band and conduction band, because this one is easier to talk about and to represent the energy levels of electrons. You know that when we have an atom, this is the in the first orbit, electrons in the lowest energy level, and then we go higher and higher. It depends on the number of electrons of that material. They distribute in that format. And we have already discussed that it's uh, easier for outermost or valence electrons to snatch them away from the nucleus because the binding force is not that much. So now suppose I give enough energy to this electron, and now I am providing energy so it can go to the or I succeed to snatch it away from the nucleus. Similarly, I give energy to this electron and I have snatched away it as well. This one is also gone and this one is also gone, and now they are almost free from the nucleus, and I can use them for conduction. If I snatch, for example, these 4 electrons out of the outermost shell of this poor atom, thus providing the energy, I have snatched them away, so now they are not bound with their nucleus, and if I apply an electric field across this material, they will just follow the path. So the first thing I want to clarify that I can make this phenomenon in another context. For example, I can say, okay, for the valence shell, and remember that the picture of the atom is not that simple. There are subshells. For example, when these electrons were here in the valence shell, it doesn't mean all of these electrons have only one energy level. Still, even in this shell, there are subshells, and electrons exist in those subshells. It is not only one orbit, and shape of the orbit is not that simple. There are subshells like S, P, D, and in those shells, energy levels they vary little bit. So instead of that, I can have a simpler picture. Instead of showing an atom and then outermost electron and then showing that I give enough energy to this electron to snatch it away, instead I can present them in the bands. For example, I say, okay, here I have valence band. In the valence band, I will imagine that those electrons are actually here in the valence band. So I will show them like this. Maybe 2 electrons exist in the upper energy level. These energy level are for the valence shell. And I told you that this shell has sub shells inside, and the energy levels, uh, they are little bit different. So now we can imagine that, for example, in one energy level, I have 1 electron, 2 exist in that energy level. And now when I give enough energy to these electrons, for example, this one, it will jump to the conduction band. By conduction band, I mean they are near to the ionization. If you see a previous picture I showed you, that when they reach near the ionization, for example, there are also sub energy levels in the conduction band or near the ionization. You can see some lines that they are near to the ionization but not exactly, they are almost free. So there are some energy levels. It's not like there is only one energy level. If you give, it is free. Even in the conduction band there are some levels, and then I give energy to this one, it may jump up to even a bit higher level in the conduction band. Maybe 1 electron goes to that, and another, after giving it the energy, it will jump to this. So now they are in the conduction band. It means they are near the ionization zone. I mean they are almost or completely free from their corresponding nucleus. So instead of saying that the electrons in the outermost shell and I snatch them away, I can present the same phenomenon in this way, that there is valence band and then these are the sub energy levels of the valence band, electrons in the valence band, and then when I give them enough energy, and what is that energy? That energy we call actually we call it a band gap, because the valence band where the electrons are a little bit loosely bound with the nucleus, and if I give them energy, we call them Eg, the gap energy, they will jump to the conduction band, any level of conduction band, and now they are free for conduction if I apply any. electric field across this material, they are free, and I will have my current flowing through that material. And this is band gap energy, and all we care about is the lowest limit of the conduction band and upper limit of the valence band. Of course, if an electron, if he's here, so I only concern about the energy between upper limit of the valence band and lower limit of the conduction band. So basically, conduction band is the area near the ionization, and there are some sub levels as well. Similarly, for the valence band is corresponding to the electron in the valence shell, and in the valence shell there are some sub energy levels or sub shells corresponding to different energy levels. So the next time, if I want to talk about the material and their properties, I will show electrons. For example, this way, like we decided for a compact shape of the electron, right? I was showing only the outermost electron. So now I will not show any image of the atom. Instead, I will show this band diagram, and if there are 4 electrons in the valence shell, I will show those electrons here in the valence band between these vertical lines, and each line represents a different energy level in that valence shell. And when I will talk that I am giving energy to this electron, so I will say like they will jump to the conduction band. And now you know that conduction band is the area near the ionization zone, where they are almost free from their nucleus and they can be conducted. It means they will, if I apply a potential difference across that material, they will start flowing. It will conduct a current. So here we have a material made of silicon, and you can see that all the atoms present in that material, or this material is made of silicon. So that's why almost all the atoms present in the material, they are silicon atoms. So this is pure silicon material, or material made of pure silicon. Another name for pure silicon is intrinsic semiconductor. Silicon is a semiconductor. So I can write it as intrinsic silicon or intrinsic semiconductor. So this is intrinsic semiconductor. Intrinsic semiconductor is made of pure material of silicon or germanium or whatever under consideration. And as I told you that what if I want to change the conductivity of this material, and I told you there is a smart way to do that, and we are going to discuss that right now. And before that, let me remind you once again that as we have seen, because of the covalent bonding, if I apply a potential difference across this material, we will not see any current flowing through it, because of the covalent bonding, electrons are not free. So I told you that a way to conduct electricity through this material is either if I apply very strong electric field so that they will push the electrons really hard to flow through the material, which is not very practical, or I can heat this material. And if I heat this material, that heat will provide energy to these electrons engaged in covalent bonding to get free from this bonding and flow in the material. So this is the effect of heat on the semiconductor, because it will break covalent bonding and then I can conduct electricity. And of course, this is also not practical because it's hard to control heat and keep it at that temperature to control the conductivity. And of course, if heat changes the amount of heat energy, the conductivity will change, and this is not what we want. We usually like to have a conductivity which is constant over a range of temperature. And like we discussed the bands, valence band and conduction band, now if we want to follow that terminology, I can say that when we apply a potential across the body, electrons are in the valence band, and I need the band gap energy, which I defined it previously at Eg, because here is the valence band and then there is a conduction band, and here is the valence band, and electrons are there. 4 electrons are there in this case of silicon, and I need this energy so that these electrons can flow through the material, and I need to give this energy, which I am calling as Eg. Once I provide this energy by any mean, for example by heat, the electrons will jump to the conduction band and we will get the current flowing through the material. So whatever terminology you like, we can express that in that terminology. So if you want to explain it in terms of valence band and conduction band, which is easier to imagine and it's easier to manage. So from now on we can talk like that, because now there are 4 electrons in the valence band and I need to give them some energy so that they can jump to the conduction band where they are free to move, and once I apply a little potential difference, they will flow through the material. Now there is one more confusing concept which I am trying to avoid, but let me give you a clue that when an electron is snatched away from an atom, that atom becomes positively a positive ion, like I discussed before when I was making or building atoms. You saw that when there is a deficiency of electron, the charge is not balanced. Number of protons and electrons are equal in an atom. When I snatch one electron out of the atom, now there is one extra proton left in the atom, because the rest of the electron will neutralize the positive charge in the nucleus with the equal number of protons. But one extra proton is left, and that will constitute a positive charge on that atom. So we can call that atom as positive ion. But in this case, the charge carrier which are flowing through the material are electrons. And now let's see what can we do to change the conductivity without giving the material energy in the form of heat or extra electric potential difference. Let's do what can we do something else to change the conductivity of this material, I mean the conductivity of semiconductors. Here is a material phosphorus. It has 16 neutrons, 15 electrons, and of course 15 protons. So here is the atomic structure of phosphorus. 16 neutrons and 15 protons are in the nucleus. Then I put 2 electrons in the first orbit, then 8 electrons in the second orbit according to the rule. And because 2 and 8, 10 electrons are in the first 2 orbits, and then I have only 5 electrons left, because there are 15 electrons. 10 are in the first and second orbit, so I am left with 5. So I put 5 electrons in the third orbit. And if I want to show this atom in my presentations, we have already agreed that I will show them like this. A simple image of this one. I will not show inner orbits or the nucleus. So here we have 5 electrons in the outermost shell of phosphorus. So here is the magic. So I will go back to my slide here. So you know that this material is made of silicon. It's pure silicon or intrinsic silicon. Okay, it's intrinsic silicon because it is made of pure silicon. Now I am going to do something. Here I have few phosphorus atoms, right? And I want to do something and see the magic here. Here I have a silicon atom and I will remove it. And I will bring a phosphorus atom in place of silicon. So now do you know what will happen if I do that? Let's analyze. Because now there was a silicon atom which had 4 valence electron and it was making a perfect bond with the neighboring 4 atoms. So one was shared with the atom on the right, one with the left, one above and one below. But now I have replaced silicon atom with a phosphorus atom, and phosphorus atom has 5 electrons in the outermost shell, or 5 valence electrons. So now how will it make a bond? Okay, so let's see how will it do it. So one electron will make a bond with the atom above, a covalent bond. Similarly, this atom will make a covalent bond with the atom on the left, and this atom or this electron will make a bond with the atom below, and similar is the case on the right. But now what will happen to this electron, because there is no atom there to make a bond with this electron? So what do you think will happen to this electron? This electron will be free, because unfortunately it couldn't find a partner to make a bond with, and it is free. Okay, so what if I do this process with some other silicon atoms? I remove this one, I replace it with a phosphorus atom. Maybe I remove another one and I remove it with a phosphorus atom. And in this way, you see, before, because every electron was engaged in a covalent bond with the neighboring atoms, so I didn't have free electrons. And when I was trying to connect the terminals of the battery with this material, I couldn't get any current flow because no free electron was available in the material. But now what did I do? I replaced some silicon atoms with a phosphorus atom. And I know that a phosphorus atom is pentavalent. Pentavalent means there are 5 electrons in the valence shell. 5 electrons in the valence shell. So it is pentavalent atom. So when I replace silicon with the pentavalent atom like phosphorus, it makes bond with the neighboring atoms, of course, with the neighboring atoms. The problem is one electron is always left because it doesn't find any neighboring atom to make a bond with. So I will get one free electron, because if an electron cannot make a bond with any atom, it is free, right? So it means I am increasing the free electrons in this material. Before it wasn't possible because there were 4 valence electrons and each electron could find a partner or could find an atom, neighboring atom to make a bond with. But now I am making free electrons by injecting phosphorus atoms into this material, and with every atom I replace, I get one free electron. And now if I connect this battery with this material, I will get some current flow. And how much current will I get? It depends how many atoms I replace with, how many silicon atoms I replace with this pentavalent material, which is phosphorus in this case. So you see, I got a smart way to change the conductivity of this material, which was otherwise behaving like an insulator. And I didn't want to use some other ways like heating the material or something. So now I have found a very smart way to change or replace some silicon atoms with the phosphorus atoms. And because phosphorus is pentavalent, mean it has 5 electrons in the valence shell, it makes 4 covalent bonds with the 4 neighboring silicon atoms, but 1 electron is always left for each atom. And that one left free electron will do my job. It will help me to run the current through this material. And now I have the control. If I want more conductivity, I will replace more silicon atoms with phosphorus atoms. So I can do that, right? And but now you know that this is not silicon, pure silicon at least. You can't say that this is pure silicon or intrinsic silicon. It's not intrinsic or pure silicon because now I have doped it with phosphorus, and you can call it a type of like mixture or something because I have replaced some silicon atoms with phosphorus. So what should we call it? So we call such a semiconductor material extrinsic semiconductor or extrinsic silicon. And because in every time when I replace a silicon atom with a phosphorus atom or pentavalent atom, I get one free electron, and electrons have negative charge, and negative is represented starts with N. So I can call this material as N-type semiconductor or silicon. So this is N-type semiconductor because I changed some silicon atoms with a pentavalent material like phosphorus, and with each replacing atom I get one free electron which is unable to make a bond with any atom because it doesn't find any neighboring atom to make a bond with. It means I get some extra free electrons in the material. So this is N-type semiconductor, and I can change the conductivity according to my desire because I can replace more silicon atoms with pentavalent material, and conductivity will increase. If I replace less number of atoms, of course the conductivity will decrease. And this is N-type semiconductor or silicon. So you see how interesting is this? Wait a minute. I am getting naughty. Let me do something else. As you remember that I have already told you about the boron atom. Here is the structure. It has 6 neutrons, 5 protons and 5 electrons, and distribution of electrons is like this: 2 electrons in the first orbit and then 3 electrons in the second orbit, and that's all. So here is the representative picture of boron if I want to use it, because I will hide inner completely filled orbits and nucleus. And now I am going to try something else. So now here I have the same silicon, intrinsic silicon material, and here I have boron atoms. And if you see, boron is trivalent. Trivalent means it has 3 electrons in the outermost shell or valence shell. And now I want to do the same process I did for a pentavalent atom or the phosphorus. So now I will replace some silicon atoms with boron atoms. So here is the first atom, and before I replace other atoms, let me see what will happen to the bonding. So here is the atom, and there are 4 neighboring atoms around this boron atom. So of course one electron will make covalent bond with the one atom. It could be anywhere. Similarly, with its second electron, it will make a covalent bond with another atom. With the third one, it will make a covalent bond with the third neighboring atom. But now it doesn't have any electron to make a covalent bond with the fourth neighboring atom, whatever it is. So what will happen? It means it will have a place which I can call it a hole, which is seeking an electron. So it will be shouting all around in the material, I need an electron, I need an electron to fill this space so that I can make a covalent bond with my fourth neighboring atom, because that fourth neighboring atom is feeling lonely. So it means it is looking for an electron. It is a deficiency of electron. And if I replace few other materials, for example, now I replace another silicon atom with another boron atom, it means now I will have a deficiency of electron. So for each atom I replace, I will always have one deficiency of electron, or a deficiency of electron. You already know that one electron is missing. It means there is a positive charge, an equal but opposite positive charge in the material overall. So it means I am adding a type of positive charge in the material. Before I was adding negative charge in the material because I was adding extra electrons. Extra electrons mean I was adding extra negative charge. But now I am taking out electron because I am replacing silicon. Silicon has 4 uh, valence electrons, but I am replacing silicon with a boron atom which has 3, or it is trivalent. It has 3 valence electrons. So of course this means I am decreasing number of electrons in the material virtually. So if I am decreasing number of electrons, mean I am making this material more and more positive, or I am increasing positive charge in that material. Okay, so once again, if I connect the ends of the battery with this at the ends of this material, current will still flow, because of course whether it is negative charges or the deficiency of electrons, electrons will flow through the material. In one case electrons were flowing through the material to go to the other end of the battery, but in this case electrons will flow to fill the holes in the material, and of course it will still constitute a current because something will flow through the material somehow. And what should I give the name to this material? So because the first time I was adding electrons to the material and it was getting an overall negative charge, so I called it n-type silicon or n-type semiconductor. But now I am decreasing number of electrons, so it means I am making it positive, so I can give it a name p-type semiconductor, right? I think this is a good name. It's a p-type semiconductor. It is a semiconductor, not a pure semiconductor. It's not intrinsic semiconductor. Now it's once again it has become extrinsic semiconductor because it is not pure silicon. I have replaced some or more atoms of silicon with the boron, or with any, or I can use any other trivalent material, and it is not pure silicon, it's extrinsic silicon, but it's a p-type extrinsic silicon or semiconductor. So you see, now once again I can increase or decrease, or I can control the conductivity of this semiconductor, and I got the control to change the conductivity according to my wish. So I am ending this section here. We have done about conductors, insulators, semiconductors, and then we discussed pure semiconductors or intrinsic semiconductors, and we also talked about extrinsic semiconductors and the techniques, how did we do that. And the next we will see the real magic which happens with p-type semiconductor and n-type semiconductor, and that's a separate story, so I will start that section separately. And I hope if you read your textbook you will understand most of the things written in your book, and you will enjoy reading the book now because you already know the related and background knowledge and concepts, and I hope you will enjoy learning. Okay, for the last time, let's talk a little bit about band diagram. In the band diagram, we represent conduction band and valence band. Valence band refer to the valence shell of a material, and then we represent the electrons in the valence shell in different energy level in the valence band, because this valence shell has various energy levels inside it. So we represent those energy levels here, and the electrons present in the valence shell are represented in the valence band in this diagram like this. We show the energy in the increasing direction towards the up, and then we show a conduction band which shows that electron are almost free, and they can conduct electricity through that material. When electron is free, we assume that it is in the conduction band. Conduction band is the zone near the ionization where an electron is completely free from its nucleus. So if we want to represent this atom, it's a conductor, it's copper. Copper is a conductor. So if we want to represent the a conductor in terms of band diagram, because this is more convenient to show the energy level than the image of or a diagram of an atom and showing the valence electrons. This is a more convenient way to show the energies. So for the conductor, we see that the conduction band and the valence band, they overlap. So it means there is no band gap energy to provide to the electron so that it can jump to the conduction band, because it is already in the conduction band. In other words, because when conduction band and valence band, they are overlapping, it means electrons are already in the conduction band, and very little, as soon as we apply a potential difference across the material, we will see the current is flowing through the material. So for conductors, the conduction band and valence band, they overlap each other. Similarly, when we talk about the semiconductors, for example, the silicon, we see that there is a band gap, and we call this gap energy, and this is the energy we have to provide to the electron in the valence shell externally so that it can jump to the conduction band, and once it goes to the conduction band, it is free to move. A semiconductor will behave like a conductor, but if in at normal situations and at lower temperatures, electrons, they reside in their valence shell or in the valence band in terms of valence band diagram, and in that way we need to give external energy to the electron so that it can jump to the conduction band, and then a semiconductor will behave like a conductor. So now, how about insulators? So you have seen that for the conductor, conduction band and valence band, they overlap. Electrons are almost free. That's the reason we don't need to give energy to the electrons from external sources so that it can jump to the conduction band, because they're already overlapping. So an electron in the valence shell or in the valence band is already in the conduction band. For the semiconductor, they are separated, conduction band and valence band, and there is a gap, and we need to give external energy to the electron in the valence shell so that it can jump to the conduction band, and then it will start behaving like a conductor. But how about the insulators? Can you guess from the trend we have just seen for the conductor and for the semiconductor? So can you guess how the band diagram or energy level diagram will look like for the insulator? So I hope you have guessed in the right way that the band gap between the conduction band and valence band will be increased. And then, of course, for an insulator, if there is an electron, we have to give high energy so that an electron can jump from its valence shell to the conduction band, and then it will behave like so. If an electron is in the valence band and we see that this energy or band gap energy is too much, we have to provide so that it can jump to the conduction band. So for the insulator, the gap between the conduction and valence band is too much, and it shows that we need to give high energy to provide to the electron externally so that it can jump to the conduction band.